Hi HMS modelers, this is Matt Fleming, work at the Hydrologic Engineering Center, and in this video I'm going to talk about the linear reservoir baseflow method. On this slide you can see a figure on your right, and in this figure, which you can see on the recession limb of the hydrograph right here, instead of what you saw in the recession baseflow method, where the recession baseflow method simply tries to model the curve or that receding limb of that baseflow hydrograph, the linear reservoir method is quite a bit different. And this method, we're not trying to simulate a curve or define the shape of the curve. The program is actually trying to model how infiltrated water goes into the soil, how it moves in the soil, and then back onto the land surface, and then flows through the stream network. And as the name indicates, the linear reservoir method is going to use linear reservoirs, a simple approach, to model that movement of water through the land, or on top of the land, into the soil, and then back onto the land surface, and then out of a watershed. The continuity equation is going to be used in this approach. So we have this equation on the left is the continuity equation. So ds over dt, that's the change in storage at time t. We have I sub t is the average inflow into the storage at time t. And in the case of this baseflow method, the inflow is going to be inflow from the loss method. And we'll talk more about that in just a second. Outflow is the outflow from the storage at time t. So this is the outflow from the linear reservoir. And so we have two unknowns in this continuity equation. And to help us solve it, we can define a linear relationship between storage and outflow. And that's what we have in this equation on the right. That's the linear relationship. We're going to use that coefficient, the R coefficient, as a linear reservoir coefficient. And so this is a parameter that you would define so that the program can solve this continuity equation. We have a couple of things on this slide. We have a figure on the right. Let's talk about that first. And so the figure on the right is a conceptual representation of the canopy, the surface. Here we have our loss method. And in this example, I'm going to use the deficit and constant loss method, where we have moisture deficit is being modeled and then a constant loss rate or a percolation rate into the soil. The bottom part of the figure, this is where I'm going to represent the linear reservoir baseflow method. And as you can see within HMS, there are going to be 3 different layers. You don't have to use all 3 layers. You can use only 1 layer if you want to. But as this figure is depicting infiltrated losses in the deficit and constant loss method, they're going to be routed to the linear reservoir baseflow method. And then as we talked about in the previous slide, the program is going to use those equations to route water within those different layers, those different linear reservoirs, to total outflow for that subbasin element. So we have the bullets here. So the linear reservoir baseflow method is designed to work with all the loss methods. It's explicitly identified in the soil moisture accounting loss method. So originally when soil moisture accounting was added to HMS, that's the same time that the linear reservoir baseflow method was added. And initially, only those two could work together. But over the years, the HMS team has opened up the capability for the linear reservoir baseflow method to work with all the loss methods. You do need to be careful, though. So for the curve number and green and amped loss methods, all losses from those methods do become available to baseflow. And so when you think about that, some of the losses for curve number and some of the losses for green and amped, those are losses due to the soil, due to water bonding or adhering to soil particles. So the soil might not be saturated, so you have that initial water being just bonded to the soil particles. It's not really gravity water. It's not going to flow through the soil. So unfortunately, with those loss methods, that water does get routed to the linear reservoir baseflow method, but there are some options, some user options that you can define to overcome the fact that all infiltrated water or all water that is lost or defined as losses from the loss methods is routed to the linear reservoir baseflow method. One thing to note, though, for the initial and constant and deficit and constant methods, You do have that moisture deficit. The program does not route any water that's captured by the deficit to the groundwater or to the linear reservoir base flow. The program is only going to route the losses due to that constant loss rate. So once you have saturated conditions, the program will route those losses due to that constant loss rate to the linear reservoir base flow method. So a little better approximation or conceptualization whenever you do link the linear reservoir base flow method to the initial and constant or deficit and constant loss methods. All right, on this slide you can see the component editor for the linear reservoir base flow method. You can choose at the top here the number of linear reservoir layers. So this is not the number of linear reservoirs in series, this is the number of linear reservoirs. Right now in this figure I've specified one linear reservoir, so you see groundwater 1 initial, groundwater 1 fraction, groundwater 1 coefficient, and groundwater 1 steps. You can define 2 layers or 3 layers, and think of those as groundwater layers that stack on top of each other. If you have 2 layers, as you'll see on the next slide, then you can define parameters for each of the 2 layers. For each of those layers, you do need to specify these 4 parameters. You need to define the initial conditions, how much of the losses from the loss method go to that linear reservoir layer, the coefficient, that K value, you have to specify that for each of the layers, and then the number of steps. And then as I have on that last bullet right here, you do not have to make sure that the fractions sum up to 1. So if you did have 2 linear reservoir layers, the fraction could add up to 80% or 0.8, and then what that would mean is that that remaining 20% of losses, that goes to some deep aquifer, and that volume is not routed to the base flow portion of the total subbasin runoff. Okay, here on this slide we see an example where we have 2 linear reservoir layers. So that's what we see in the figure right here. We have that constant loss rate is being directed to groundwater layer 1 and then groundwater layer 2. I've specified different groundwater coefficients for each of those layers. So 24 hours is the groundwater 1 coefficient and 80 hours is the groundwater 2 coefficient. And then look at the fractions. So groundwater 1 fraction in this example is 0.4, and then the groundwater 2 fraction is 0.6. And then what that means is that 40% of the infiltrated water is going to the linear reservoir within layer 1, and then 60% of the infiltrated water is going to the groundwater 2 linear reservoir. And then on this slide, I wanted to show some examples of how the groundwater 1 coefficient would impact the results from a simulation. I have 3 different simulations, and you can see I've varied the groundwater 1 coefficient by really a factor of, I've doubled it for each of the simulations. So the very first simulation had a groundwater 1 coefficient of 12 hours. The second simulation had a groundwater coefficient of 24 hours. And then finally, the third simulation had a groundwater coefficient of 48 hours. And that's the dashed line right here. You can see that as the coefficient increases, the magnitude of the base flow hydrograph is much smaller, but it's spread out in time. So it's showing that those coefficients impact the attenuation of the base flow hydrograph and can spread out the contributions from base flow over a much longer duration. One thing to point out too is notice how that groundwater coefficient doesn't really impact the timing of the hydrograph. You notice even though I vary it from 12 to 24 to 48, the timing of the peak base flow does not shift that much. So if you did need to impact or modify the timing of the base flow hydrograph, you're really not going to get to that by adjusting the groundwater coefficients. Instead, what you're going to need to do is adjust the groundwater steps, the number of steps. And what this number of steps means is this is where you would have linear reservoirs in series. And in this example, I have 2 steps. And what that means is the very first linear reservoir has a coefficient of 24 hours. So water from the loss method is going to be routed through that linear reservoir. The coefficient is going to be 24 hours. And then it's going to be routed through a second linear reservoir. And then that second linear reservoir is going to have a coefficient of 24 hours as well. And so in this example, you can see I have 1 step for the very first simulation, 2 steps for the second simulation, and then 3 steps for the third. And now you can see how the timing of that Baseflow hydrograph is shifted based on the number of steps or the number of linear reservoirs I have in series. On this slide, I wanted to show how the groundwater 2 coefficient might impact the computed results. And the figure on the left shows I have 2 linear reservoir layers, groundwater 1, groundwater 2. The groundwater 1 coefficient is 24 hours, groundwater 2 coefficient is 100 hours. And then 50% of the water from the loss method is going into groundwater 1, and 50% is going into groundwater 2. And the way that this is set up conceptually is groundwater 1 is going to represent interflow, and then groundwater 2, with that larger storage coefficient, is going to represent the slower responding baseflow portion of the runoff hydrograph. And so you can see on the figure on the right, based on 3 different simulations where I varied that groundwater 2 coefficient from 100 hours to 200 hours to 300 hours, you can see the impact on the total base flow. Again, this base flow right here, it combines both groundwater 1 and groundwater 2. And you can see that the groundwater 2 coefficient is not going to impact results much because look at these values. These values are rather large, 100 hours to 300 hours. And so think about this as that groundwater 2 contribution is really spread out over a much larger duration. And so groundwater 2 will not have much of an impact on the magnitude of any of the flood hydrographs. It's going to have more of an impact on the recession, the longer duration recession portion of your baseflow hydrograph. Okay, the figures on this slide show some examples for how the groundwater fraction is going to impact the computed hydrograph. I have 3 different scenarios here. I have a scenario where the groundwater fraction is 1, so that means 100% of the losses are going to be routed through baseflow and then combined with the total runoff, or made up of, added to the total runoff from the subbasin element. And then simulation 2, 50% is lost. It goes to some deep aquifer, and then 50% is routed through the groundwater 1 linear reservoir, and then simulation 3, only 10% of the infiltrated water, or water from the loss method, is routed through the linear reservoir. And so you notice the shape really doesn't change that much. It shouldn't change that much. We're using the same storage coefficient for each of these 3 scenarios, but the volume is changing drastically. And you can see the baseflow volume changes from 1.6 inches when 100% of the losses goes to the baseflow hydrograph to just 0.2 inches when only 10% of losses goes to the baseflow hydrograph. And so the take home on this slide is that groundwater 1 fraction, this is going to be one of those calibration parameters or tuning knobs that you can adjust to help you better match any observed volume that you might have from gauges within the basin model's domain. And then the figure on this slide, or figures on this slide, show the different options for initial discharge. So just like the recession baseflow method, you can choose discharge per area, or you can define the discharge explicitly. And then so what a discharge per area value of 1 CFS per square mile means, if your watershed has a drainage area of 100 square miles and you specified 1 CFS per square mile, then the total initial flow at the very first or at the very beginning of the simulation would be 100 CFS. I generally like to use the discharge per area option because that is somewhat consistent across a basin model or consistent across all the subbasins upstream of a observed flow gauge. You could look at the observed flow gauge at any point in the watershed, and if you know the drainage area at that flow gauge, then that could be used to help you define the flow per area for all of those subbasins upstream of that gauge. The plot on this slide shows 3 different scenarios where I've modified the initial discharge per area. So scenario 1, 1 CFS per square mile, 5 CFS per square mile, and then 10 CFS per square mile. And then you can see how that those specifications impact the computed results. You'll notice that not only does it impact the very beginning of the simulation, the initial conditions also impact the magnitude of the flood hydrograph as well. And then in this last bullet, I like to be strategic about the starting time for a simulation. If you start a simulation so that it's been some time or some duration since an antecedent event, then you don't have to worry about interflow or groundwater 1 flow. And if you do that, then you could specify a groundwater 1 initial discharge per area of 0. So the only thing that you're modeling is that slower responding groundwater flow. So that's one way to be strategic and limit the number of parameters or initial conditions that you have to define for a simulation. And then finally on this slide, you can see the linear reservoir baseflow method can be used for continuous simulations. It was originally designed for continuous simulations. This method is going to conserve mass. Again, water that is infiltrated or lost due to computations from the loss method are going to be routed through those linear reservoirs, so you're not going to have to worry about the program computing more runoff volume than precipitation volume, which is nice and appropriate. And then you also notice on this slide, the linear reservoir baseflow method can be used to simulate or model both inner flow and that slower responding groundwater flow. You have the option to specify those coefficients that can be used to simulate inner flow, or this portion of the runoff hydrograph right here. And then you have a separate option, groundwater 2 or groundwater 3 if you need to specify the slower responding or flatter portion of the baseflow hydrograph.